Okay. Okay, hi everyone. I'm just going to start with my video on just to say hello so you can see me. My name is Dominic Henry. I work for the Endangered Wildlife Trust, but I'm also an HRA at SEEC. I did my postdoc at SEEC for a couple of years working on the Karoo Biogaps project. So just looking at the list of participants, I've met quite a few of you. So yeah, welcome to today's toolbox. My internet is very, very unreliable. So I'm going to turn off my video and switch to my mobile data. So hopefully you don't lose me during the talk, but I also just want to make sure I don't run out of data. Also, I'm a bit of a cheapskate. So, okay, I think we're a couple minutes past. I see there's a couple of people still coming in. So I'll give it maybe one more minute and then we'll give it a go.
Cool. Just a note on the questions. We'll have a question and answer session right at the end. I think that makes it easier for the flow of the talk.
Okay, let's see. Okay, so, I think I'm going to go ahead. You should all be able to see the presentation. I will try and monitor the actual chat, so if there are any issues during the presentation, just feel free to actually put something in the chat. Okay, so today I'm going to talk to you about time to detection occupancy models, and a lot of this work, a lot of what I did in my postdoc, I actually used these models, and pretty much everything I learned I did during that period. So yeah, I hope to impart some of the things I've learned and the workflows that I've developed to use these models. So before I go on, I'd just like to mention that the previous toolboxes that we've done at SEEC have focused on different facets of occupancy models. So we've had 4 talks before mine on the occupancy model theme. So Rez Altweg, Alan Clark, and David Mapisa have all contributed to these talks. So you can see in this table the different facets. We've got talks that were focused on static and dynamic occupancy models, as well as doing them in the Bayesian and maximum likelihood frameworks. So if you look at if you download the presentation, I put a URL link in this column, so you can go directly to those talks, or you can just look on the SEEC website; they're all there. So what I'm going to talk about today is focus on multi-species model. I'm going to do a single season modeling structure using continuous time data in a Bayesian framework. So I've got quite a lot of material that I would like to cover today, which means I won't be able to get to too many of the basics. So if you need to brush up on occupancy models, there's a lot of material that's on our SEEC website. So just the outline of the talk, I'm going to introduce the background of the models and just talk a bit about their formulation and how they've been used. I'll then run through the markdown documents. I've got 4 markdown documents that will handle the next 4 points here. So the first is just running through a single species time to detection model, then looking at data processing from a real field data set that we've collected, and then how that can feed into the actual multi-species model in the Bayesian framework, and then how the next step would be plotting the outputs and the parameters and predictions, and producing some nice graphics to visualize all of that. Okay, so just a quick recap of the occupancy model and to understand the structure of a typical occupancy model. We just need to remember that one of the reasons that we use occupancy models is to account for imperfect detection and just to get a better handle on the true state of occurrence at sites in which species are not detected. So what's important is also to try and understand the environmental factors that drive these patterns of occurrence. So essentially what we start with is detection, non-detection data traditionally in this part here, and those data feed into our occupancy model, which has a hierarchical structure. which composes of the observation and the occupancy model. And when we use that model formulation to then make inference and predictions on both the ecological processes and the observation processes. So that's generally the structure of it. So one thing I always pretty much include in talks that I've given about occupancy models is this slide. And it's a topic I think is really important, and we need to always keep in mind the numerous factors that affect detection during our surveys. And I think it's especially important at the beginning of your designing your study to really think hard about your study species and the places that you'll be surveying, and just to understand that, you know, whether a species tends to be more or less difficult depends on a large group of nested factors, starting with the actual species characteristics, and then factors that relate to where they occur, and then any temporal variation in that occurrence, and then the survey characteristics. So a lot to think about there. So if we think about the typical data requirements for a typical occupancy model, we normally work with detection, non-detection data, so ones and zeros, and we normally replicate those surveys through time. Although we can do a single visit using detection, non-detection data, we normally need to either then use multiple observers or use a spatial subsampling approach. There is another option that technically can be used with a single visit, and that's where we collect continuous time to detection data. So that essentially is the time that we detect a species after we've started our survey. So it's normally the time to the first detection. So a very simple way to understand the data structure there. So from there, this idea of using time to detection data was first proposed in 2008 by a group of Australian researchers, and they were interested in understanding the relationship between survey effort and plant detectability in the context of environmental impact assessments. So they wanted to make sure that we were actually looking hard enough for some of these more cryptic or rare species. So they described this general model for the detection process, which was actually only later introduced into the formal hierarchical occupancy model itself. So they didn't really focus on estimating occupancy, but mainly patterns of detection. So to illustrate this, we can look at one of the figures from their paper, which basically shows how this time to detection model was able to be used to assess how long an observer would have to look on the x-axis here to reach a certain level of detection probability here on the y-axis. So, and the shape of these curves is governed by the lambda parameter, which we'll come to, but essentially this just shows you how after a certain duration, we can expect a certain level of detection based on species characteristics or survey characteristics. So this was actually a simulation, but if we look at an applied example here for this species of plant, they've actually got 3 of these detection curves, and they're based on a combination of server ability, the time of day, and the weather conditions. So depending on whether those conditions are good or bad, we actually see that we need to conduct surveys for much longer to get a similar level of detection. Okay, so just to actually introduce the model formulation now, as I mentioned, these models have been integrated into the occupancy model frameworks. And if we look at the state process, this is exactly the same as the traditional occupancy models, but what is different, obviously, is the observation process here. So here we model time to detection, Y, at site I during survey J for species K. So I've just put the notation here so you can keep track of it. So time to detection, we model that as an exponential random variable with an expected value of lambda here. And it's important to note that this lambda is the expected number of detections per unit time, or the detection rate. And this parameter is actually censored at Tmax. So Tmax represents the maximum survey time, or where the survey ends. And I'll come back to that in the next slide. So once we've estimated this lambda parameter for each species, we're able to use it in combination with a survey duration D to work out the actual detection probability here, P. So we're able to either do that in a point format to take one data point and figure out what the detection probability is after a certain time, or we can take a vector of durations to work out those detection probability curves, which I showed you in the previous slide. So just a bit more on the actual censoring of that data, as I mentioned. So one of the complications, obviously, is with this model formulation is that whenever a species is not detected after the maximum search time, or there is uncertainty about the state at that site. So we need to use this censored variable. And to do that, we use this indicator variable, which is derived from this model over here. And it basically says that when time to detection is greater than the maximum survey time, but the site is occupied, or if the site is unoccupied, then we treat this time to detection as missing, so NA value. And if that censoring indicator is 0, then we can actually model it as the exponential value. Because we don't have a detection, non-detection data, we either have a 0 or 1, but we obviously can't have a value for time to detection if we didn't find anything. Okay, so that's more of the technical thing. It's not too much of an issue to deal with. I thought I would just explain the Weibull distribution. Just to bring this up quickly, there is another option to use instead of the exponential distribution. And essentially what this Weibull distribution does is it allows us to change or to assume that the detection rate varies over time. So the exponential is a constant rate, whereas this Weibull has another parameter, the shape parameter, which can estimate how detection rates change over time. And this hasn't really been widely applied. I'm only aware of one paper that's actually incorporated it, which I've put here, this Medina Romero paper. It's quite interesting. It compares the differences in the estimates between the Weibull and exponential distributions. And it's a bit tricky to think of in which cases this might work, but I'll leave that to you if you ever design a study. But one thing we could assume is that if we walk into a piece of habitat where a bird occupies a territory, and perhaps that bird is quite conspicuous and it becomes aware of the disturbance of the people surveying the area, it might become more shy and therefore less detectable as the survey continues. So there might be some reasons where you might want to use this distribution instead. But I haven't worked with it myself. Okay, so the key question here is that given that in theory we can use one time to detection survey, the key question is can we really reduce sampling effort and get reliable estimates? And since this 2008 paper was introduced, there really hasn't been a lot of uptake of this method, and it's a bit unclear as to why this is, seeing as it offers such potentially good logistical benefits. So anyway, to address that, Bornand et al. In 2014 decided to look at a paper where they compared detection, non-detection occupancy models with the time to detection occupancy models to see whether it actually provided a good fit. And this is just a figure from their paper. Essentially on the x-axis for all of these, we've got the estimates from time to detection, and then they had estimates from their standard occupancy model. So they were surveying vegetation plots, and a one-to-one line here would indicate that the estimates line up quite closely. So they showed that there were some places where actual detection was underestimated using time to detection data, but then as the survey time increased, they showed that they line up pretty well. So that suggests that, and their conclusion was that it works, these methods work quite well and can easily be substituted. So we looked at that, and in the context of our work on the Karoo Biogaps project, we thought, well, is this a method that we could use? And we wanted to test, well, how robust is this method? Our study was very different from Bornand's paper. They used vegetation plots with species that had high average detection probabilities, and we were working with bird community data over a very large spatial area. With a much bigger variation detection and occupancy probabilities for each of the species. So these are just two little figures from the simulations that we did. We used simulations and field data. So on the y-axis here, it's just the mean square error. So anything that is lower is actually better. So we compared, like, if you do one time to detection survey versus doing two detection non-detection surveys, what comes out better. And for rare and inconspicuous species, we found that, okay, it looks like time to detection surveys actually perform quite well. But if you change the characteristics of that species, they actually look like they don't perform as well as detection non-detection surveys. So that was the simulations. When we applied it to the field data, the results were quite clear. This is the estimate for detection for the whole community, so the community level estimate. And this is for using one survey, one time to detection survey, and this is for using all of the surveys. And for some of it, we had up to 18 to 20 surveys. And what this shows is that the estimates are very, very different. And there's some like huge bias here with the occupancy probability as well. So we suggested that our field data said one time to detection survey was simply not adequate to actually get close to the true values. Okay. So with that in mind, how can we do time to detection modeling, and what options do we have? So the unmarked package, I recently found out a couple of weeks ago, they have implemented a time to detection function. So that allows one to model it for a single species. So the pros are that it's built in, it's fast, easy to use. They have implemented a single and multi-season variation of the model, so that's very good. The cons are that you can only work with a single species and it's not very customizable. So in a Bayesian setting, obviously there's a number of softwares that you can use to do the modeling. I'm going to focus today on Nimble, which is very, very similar to JAGS and Bugs. It uses very similar notation, but just the functionality is slightly different. So there's lots of pros to doing it in the Bayesian setting. We can have multi-species models, we can include random effects, custom distributions, and really anything that you can think of. I mean, these models can be made as complex as you want. Along with that, obviously, does come some of the cons of having to write it out manually. The runtime can be quite long, especially for these time to detection models. When you are debugging the model formulations, you often get very unhelpful error messages, and obviously the computationally, it can be very computationally intensive. Okay, so what I'm going to show you is just a couple of slides here of the actual applied example, the results from the applied example and the data that I'm going to work with. And just to note that all the data and all the code is going to be available. It is on my GitHub repo now, so you'll be able to run all of this and explore how the methods work when you have a chance. So we, with Alan Lee, and he did all of this field work. I hope it was 1 or 2 sites, but we basically had 60 odd pentads across the Karoo area. And we wanted to sample these and then make predictions about species richness and occupancy across this whole survey area. So we used 4 occupancy level covariates: NDVI, terrain ruggedness, elevation, and rainfall concentration, and then these detection covariates. So survey level covariates of wind, cloud, temperature, Julian day, and time of day. So just to show you the model formulation, so you have this in mind when we go through examples, it's very simple linear models here. We just have each of our predictors in there, and we did have a quadratic effect for time of day because we thought detection birds, they are more active in the morning and evening, so we thought there might be an effect there. Okay, so some of the results from that that we're going to be able to generate, but I just thought it would be good to have a picture of what they look like now. This is just a summary figure, so the number of detection events for some of our species. We're also able to get the coefficients for our detection submodel to figure out what had significant effects on detection. We're able to estimate the lambda parameter with credible intervals for all of our species. as well as generating detection probability curves, which can be used in subsequent analysis for designing surveys. And we're also able to look at random effects and see how different species respond to the different occurrence level predictors. So I'll explain all of that in a bit more detail now. What I'm not going to talk about, but what we're able to do with this model formulation that I'll introduce, is to create occurrence maps with uncertainty associated with each of those. So we've got a mean and then 95% upper and lower bounds here, and then combining all of that to get an actual species richness map across the whole area of a whole community. So there's a lot you can do with these outputs. Okay, so I'm now going to move to actually showing you the Markdown documents. Is everyone, it's hard to know if everyone's still there and this is all still working. Just going to take a break to have a sip of coffee here, but can someone just let me know? It's such a weird thing to have it so quiet. Okay, everything's still working. Great. I can see the chat there. All right. So the first thing I said is we'll look at the single species time to detection models. So essentially, I've got the libraries over here, and let's just make this full screen. I've got the libraries and just a description with what all of them are needed for. So I suppose one is a special mention here is this HM book. So this is Mark Carey and Andy Royal's Applied Hierarchical Modeling book. So it's a textbook that I've used for a lot of this stuff, and it's a very good textbook, and it comes along with a package that includes a lot of functions to simulate a bunch of data, occupancy data, distance sampling data, and so on and so forth. So the first thing we want to do, just for this example, is to actually simulate some of the data. So we use the SIMOCTDT function from the AHM book, and these are the actual default parameters, but I've just written them out here just so that you can see what we're able to specify. So the simulation allows us to specify the number of sites that we're sampling, the mean occupancy probability, the detection rate, as well as the slope of one continuous covariate for the occupancy process and one continuous covariate for the detection process. And then we're also able to give a Tmax, so the time that our survey ends. So this basically does a bunch of, or creates a simulated data set, and you get a plot showing the frequency distribution of the measured time to detections. It also tells you how many sites are occupied based on your inputs there. And then it also shows you the number of sites at which the species was detected. So the alternative way to generate exactly the same data set is just to run that command that I've highlighted there, because those are all the default arguments. So if we just have a quick look at what those data contain, it obviously gives us just some of the inputs that we specified, but it also gives us then the covariate values for each of those 250 sites, as well as the time to detection values for each of these sites. So the first thing we'll do is actually run the model in unmarked. So this is the most simple, straightforward way to do it. Unmarked treats NAs a little bit differently to what they would be treated like in the Bayesian setting. So you can read this description, but essentially we have to just replace the NA values of the time to detection vector with the Tmax, so the maximum survey time. And if you've run occupancy models in unmarked before, you'll be very familiar with this unmarked frame function. And here that's just been modified for the time to detection process. So we just put in our response variable, the survey length, as well as the site covariates. And then we've built that unmarked data frame. We can have a quick look at it just to make sure everything looks right. And here it does. And then we can actually fit the model using this OCTDD function. So we've simply given information about which covariates to assign to which detection and occupancy side, and then you've just given the formula there. And then so that fits very quickly, obviously, and we can just then have a we can have a quick look at the output, and we can then extract these estimates and just compare them with the truth, the real values. So that's what I'm going to do here in the summary table, is just extract those parameters. And now remember, the intercepts are not on the probability scale, so they need to be back transformed, which you can see how I did in this section of code. But then this summary function just creates a little table, so we're able to see, okay, this is the truth, this is what we specified in the simulated data, and this is the estimates that we get from the unmarked model, and they seem to correspond quite closely, so that's fine. We know things are working there. So with using functions from the unmarked package, we're able to also extract the lambda value. So that's our detection rate parameter. And then we're able to do that with this function here. We're able to set then a survey duration and then use this exponential distribution function to get our detection probability after that survey time. So that we could work on a point format, or we can just specify the survey duration as a vector with as many times as we want. There's also a built-in function to actually get the probabilities, a list of all of the probabilities from the model fit here. Okay, so now I move on to specifying the same model in Nimble, and we'll use exactly the same data set, but we just have to package it a little bit differently. So to put all the data together for the Nimble model, we'll just make it a list, and I've described here exactly what we need to input. So it's pretty much the same: the time to detection data, the censoring indicator, the covariates, etc. Again, we just have a look at that list, and it gives us all of the, just gives us a chance to check that everything makes sense. Okay, so this is the actual, the model that we need to define. So in Nimble JAGs, you would normally sync this, you would write it all out and sync it to a text file. But the Nimble code function, we're able to actually write it in R and to run it as a function. So it just makes things a little bit easier to see that we haven't made any errors in the syntax, or we're not missing any brackets or anything like that. So I think if you need to catch up on what the priors are and why we need to specify them, I would say look at Rez's talk that he did on introducing Bayesian modeling for the occupancy stuff. So here I won't go too much detail what the priors are about, but we set them first, and then we just we have the likelihood function where we have our model for occurrence here, which would be the same as a standard occupancy model, and then we've got our time to detection model here. So here we've just seen that we're modeling it, our time to detection value as an exponential random value governed by the lambda parameter here, which we model as a function of our covariate A, our first covariate. And it's obviously got the intercept, and then this is the model for the censoring of the data that I explained in the slides. Okay, so that's pretty simple. It's, it closely resembles your standard occupancy model that you can formulate. We have to then provide initial values for a lot of the parameters that we include. So we set all of the Z parameters to 1, and then provide the time to detection starting values as censored rather than non-occurrence. So Tmax plus 1, so something that indicates it was beyond 1. We then choose our parameters that we want to estimate or monitor during the process, and then indicate our MCMC settings, so our iterations, thinning, burn-in, and chains. We can then fit the Nimble model using this Nimble MCMC function, and the arguments are quite intuitive. We have to supply the code, the constants is the nim data, the initial values, which parameters we want to model, and then all the MCMC settings. We want to set summary equals true. It gives us a summary of the values of the posteriors across all of the chains, and then we can make sure that it outputs the samples in the coda or MCMC list format. Okay, so that you can run that, and it runs quite quickly. It gives a bunch of warnings, but I'll come back to that a bit later. But they're not errors, they're just warnings. So we're able then to take that model fit and then extract the summary from all of the chains and extract the parameters that we wanted to compare. And I've just added that to our summary data frame, and we can see that the estimates again match quite closely the actual truth. So I think this is just useful to see how the basics of these models work. And if you have a single species that you're working with that you're able to use this kind of model for, then I hope this actually helps. I started using JAGs when I started doing these analyses, but I experimented just recently with Nimble, and I found that the benefits are massive in terms of computation time. So I'll just start with this comparison here. So this is comparing JAGs and Nimble in terms of the efficiency, so the number of the effective sample size per second. And this simulation is actually run for that model I've just presented above. And you can see that Nimble's almost, in this case, for the mean, it's almost twice as fast as JAGs. That does change with the parameters that you actually estimate, but I've seen massive gains in how efficient and how quickly you can run these analyses, especially with big data sets. So it's not a difficult switch to make if you've been using JAGs. There's a lot of good documentation. I've put a bunch of links. So this is the home page. And they've got a very user-friendly and welcoming Nimble users Google group. The Nimble ecology package actually has built-in functions. I haven't explored that, but it's an extension of the Nimble package. I've explained some of the, or linked to the instructions for installing. There's a couple of things you need to do, especially if you're using R 4.0. But it's all explained there. And then they've got some helpful articles explaining how you can convert your existing models in JAGs, OpenBugs, or WinBugs, and how to do that. I haven't worked with how to parallelize or do these chains in parallel. So it's fast even not doing it in parallel, but I mean, obviously it'll be 3 times faster if we could do it in parallel, but there are instructions on how to do that. Okay, there's also the paper that the authors of Nimble have just released in Ecology and Evolution that explains a bit more about everything. So a lot of resources, and it should make the switch, should you want to, quite easy. Okay, let me just check the chat here. I think the function unmarked uses code initially written by Prof. Haynes. Okay, Ellen. Okay. Right, let's see. So now I'm going to just work through the field data, processing the field data that we use for the multi-species Nimble models. And again, you'll be able to download all of this. So first thing we want to do is just import the bird data set. And essentially, this is a list of observations of bird species that were recorded in each of our surveys in each of our sites. So Pentad is a site. If you're a birder, you'll be very familiar with what a Pentad is, but it's just a grid cell in which we record bird species. So we have a number of replicates that we did within that Pentad, and then we've got the date and time at which that record was made. We then have detection covariates. So for each of those surveys, we measure temperature, cloud, wind, time of day, and Julian day, which I explained earlier. And then we're also able to, with remotely sensed data, extract site covariates. So when you read in that data frame, you'll see that we've got rainfall concentration, elevation, terrain ruggedness, and NDVI. So those 3 data CSVs will give you all the data you need to run the code below. So the first thing we want to do is create our actual time to detection data frame. So essentially, we just need to run this function to extract a bunch of start times for each of our surveys. So obviously, that's the most important thing, is to understand when did we start. Once we've calculated that, we can then join those start times to our initial bird data frame, and then use one of these mutate functions just to actually calculate the time to detection. So that's simply the date at which it was recorded minus the survey start time. And that's our main variable that we're working with here. You can do a little bit of wrangling with that. One of the important things you need to do is understand that we recorded the same species multiple times throughout the throughout the survey. So you actually, in the case in which you do that, you actually just need to filter out the first observation. So just order them and then select the first one. So that'll be time to first detection. Okay, and then you can just have a look at that to make sure that you've got your survey ID, your site, your species, your actual time to detection value. And then I don't know why I kept these two, just maybe for good luck. Okay, so if you've got a high number of species, you might want to, depending on the aims of your study, you might want to remove some of the rare species. We had a lot of species, and to make this model a bit more tractable, we had to remove some of the vagrants and rare species. So we filtered it out, well, for this exercise, I filtered out anything that had less than 20 observation records. And that's 20 over 20 detections over 1,000 surveys. So they really were singleton records here. So once we've done that, we remove it about, this is a list of them, we remove about 146 species. So we just do that by filtering out our time to detection data frame. The next thing we need to do is just order the detection covariates. So to make sure that they align with what we have in our time to detection data frame. And then we need to create some variables and arrays to structure the data. So the first thing we want to know is run this function here, just to say, okay, how many surveys did we have in each of our sites? So we need to be able to, we need that information for the next steps. And here we just say, okay, we can see we had on average we probably had about 17 surveys per site on average, but they did differ, which is important. We then need to just pull out vectors of the actual pentad IDs and the species names. So this we just work from the data frames that we've specified above. We also need to figure out how many species do we actually do we have in total. And then all of these values here are just used to actually create the dimensions for the time to detection array. So we set the dimensions of the array over here using the number of species, number of pentads by the number of counts, and then have a separate one of those for each species. And then we can just use the variables above to give those dimensions names. So again, we can just have a check to make sure those dimensions match up, and then have a look at the dimension names to check that everything looks good there. So once we've done that, we can create, in a similar way, create arrays for covariates. And then this is the important part here is actually populating the arrays. So I just created this loop function, and this is was a stumbling block when I initially got the data. Was just figuring out the best way to do it. And there probably is a better way or a more efficient way, but this was just easy for me to actually visualize and make sure all the steps worked. So it's essentially saying for each pentad, extract all the data for that pentad, both time to detection and covariate data, create a unique vector of the survey IDs in there, and then go through each of those survey IDs and extract the time to detection data and the species with which that occurs, and then fill this Y array with those data. So you can look at this in a bit more detail if you want to download the files, but just know that this is the way that we fill up those Y arrays. We create the indicator array also just by replacing anything with that was missing with zeros or ones. And then we're able to actually look at the arrays and check that everything looks fine. Okay, I see that the time is, I've obviously planned way too much to present way too much work here, but I'm just going to then run through the actual modeling. So this is the important part, and then I'll briefly look at the plotting of the objects, but again, all of the code should be quite self-explanatory. Okay, so just at the end of this document, we've just written the workspace, which has a lot of the objects that we need to work with in the next step. So this is the actual, the model stuff that we're going to do. We're going to just load that workspace. We're going to scale our covariates, just so they're all on the same scale. I think it helps with mixing, and it's just generally a good idea. We're then going to define our time to detection model. And because we have the model that has random effects, it looks slightly different from the single species one I introduced. But I'm just going to skip down past the priors to the actual occurrence and detection models. So in this section here, we just loop over each species and each site, and we've got random intercepts, so indicated by K, random intercepts and slopes for all of our covariates. So we're able to get these estimates for each species. And then our time to detection model here is where we have our detection covariates. And we had our lambda parameter as a random effect, but then we assumed that the detection covariates operated in the same way across all of the species. We're also then able to get derived quantities quite easily. So here we're able to work out how many species occur in the sites, as well as estimating the lambda, as well as their detection after a certain period of time. And we can also then work out how many species, this is how many sites were occupied by each species, and this is how many species occurred at each site. I've written out manually a lot of the priors. So you'll have to look up, I put a reference here, and this is the reference on which I based a lot of the prior choice. I'm not going to go into it now, but they've got a really good section and it's freely available. I put the reference over here, so you can follow this link. And for me, it was one of the clearest way for understanding the way to select priors for these models. There's also recently been a paper on the use of Bayesian priors in ecology, so that's also very interesting. And you can have a look at that paper and decide how to more smartly use your priors. We then just need to look at the parameters that we want to monitor and just define them there. We want to assign the constants. So for nimble models, we want to basically just give the structure of the data. We say, this is how many species I have, and this is how many surveys, this is how many sites, and this is the T max, our survey length. And then in another step, you'll compile the data. So essentially the data can change. You can specify the model with these dimensions, but then you can use different sets of data to run the models, which has its own pros or cons. Initial values, I won't spend too much time on here, but this is just putting initial values for some of the time to detection data, which you can look through. It's pretty self-explanatory. And then we need to create a list of initial values for all of the other parameters. So JAGS is really good at coming up with initial values for a lot of parameters that you don't specify. But one of the things about Nimble is that it requires you to be a lot more explicit about your initial values. So you can read up, they've got some good help documentation that explains that, but you need to read up about that. So we can build the model using the Nimble model function, and again, just supplying all of the data that we specified above. The next step is to use the build MCMC function, which puts that model together with the parameters. We can then compile the model. So just again, using these functions in this order, so that generates and compiles the C++ code, which is why I think this is quite a bit faster. We can then put our settings in. If you want to run this, I've just put a test settings here with just a small number of iterations to see that it works. And then you actually use the run MCMC function to put it all together and get it running. You can actually monitor, I've just put the timings in so you can monitor each one of those. And the main thing to do once you've done that is to keep this object, the run MCMC samples, which we use for the plotting. Okay, so I see we are a bit short on time here, so I'm just going to go quickly through the plots. I think what I'll do is just hide all the code up here. And just know that once you import your time to detection array data that you created in the first and the second step, as well as the model fit data, which is just those samples, you can create all the plots below. And those plots include some of the summary stuff we see. So just a histogram of our actual data. So the time to detection data. We might want to look at mean time to detection, again, just exploratory plots of it for some of our species. We might want to know the detection events, the number of events that we have for each species. And then looking at the actual outputs, we've got some functions in a package to get some elegant diagnostic outputs for the models. So we're able to, with this MCMC Viz package, very easily actually show you the code. It's literally this one function that provides a lot of the information that we need, and it can compile it all to a PDF, which is super useful. We then we need to just create a plotting data frame for all of the, so that we can create some of the parameter plots. And we can get things like the time of day, all the covariates for the detection level. We can get these predictions specified over whatever values or ranges that we want. Again, we can look at our parameter values. We can generate the species detection curves. And then again, for occupancy, we can get our point estimates, and these would be the community level point estimates. We can get our predictions, again, in a similar way to the detection stuff. We can also get our random effects plots. So these are really interesting if we want to see, our predictions here suggest that there really doesn't seem to be much of a community level effect of NDVI. But if we looked at the random effect plots, we'll see that there are many species that have a higher occupancy probability in areas that are very dry, and many that have higher in areas that are wet or more productive. So, and that makes sense because we have arid zone specialist birds and ones that have an opposite response. So this, again, just allows us to interrogate the data a little bit more carefully and understand how our community responds. We're also able to get species probabilities to plot those out. These are the derived parameters, the number of sites, and the species richness for each of our sites. So I've got a bunch of helper functions just for all the plotting. So just know that this is a lot of code. I'll just show all the code and just quickly scroll through like some of the plots. I've got all the ggplot data. These are all done in ggplot. So especially like something like the random effects is quite a lot of code to actually get it all working, but I think it's pretty straightforward, and you should be able to tinker around and play with it as you see fit. So let's just quickly go back to the recap here. So I think time to detection really has good potential to provide a robust and cost-effective alternative to detection, non-detection models. The detection curves are a very useful byproduct of this whole process. But what's important that we found in our paper, and that becomes apparent, is that we don't think that one survey is ever going to be enough. So some replication is important, and we showed that even doing 2 time to detection surveys is really a lot better than a single one, and still possibly better than doing 4 detection non-detection surveys. And we need to think carefully about the nested set of factors that influence the detection. So again, very important at the project design phase. And then maybe important to think about the viable distribution and whether we would expect any change in detection rate during our surveys. Okay, so I just